Hello, in this video we're going to continue our journey through the structure of matter, particularly in nuclear physics, by looking at the strong interaction. This is something that we've mentioned in previous videos, and then after that we need to look at binding energy and mass defect because they're just critical to understanding everything in nuclear physics. So, as I say, we've mentioned the strong interaction before. So when we were going through our standard model and laying out all of the different fundamental particles, then we were saying, so with the strong interaction, this is something that is described using quantum chromodynamics. And this is an interaction that is experienced by particles that have got color charge. That's what it's referring to here. So the chromo in quantum chromodynamics, that's the bit that links in with the color here. It's the same descriptive term. And if you recall from our picture that we drew up of the standard model, this means quarks and things that are made of quarks. So that will be hadrons, baryons, mesons, because they are all quark based bits of matter. So that's what we're looking at here, and it's particularly important because this is the nucleus of all of the atoms that are around us. They're made up of quarks, all of this stuff. And if we go back to looking at what was going on with the nucleus, we had Rutherford. He did that scattering experiment where they were firing, well, it was Geiger and Marsden who did the experiment under his supervision, and they were firing those alpha particles at the thin bit of gold, and they were seeing that some of them were bouncing back, most of them were going straight through. And then there was that conclusion, well, maybe most of what's going on inside the gold, mostly that is empty space, and then we've got these small concentrated regions of positive charge. So this is different to J.J. Thomson and his sort of tentative idea of a plum pudding model, where you had this sort of continuous blob of positiveness with these electrons stuck in it, and that was what was going on inside an atom. But once they kept on investigating all of this, and they saw that this description of the atom was actually more accurate, and you see that you've got these protons and neutrons inside the nucleus of the atom, well, what is it that's holding these things together? We've got a problem with the protons in that they're all positively charged. So you've got electromagnetic repulsion between these, pushing them all apart, and yet they exist inside the nucleus, all held together. And you've got, similar in a lot of ways problems with I've written nucleon, neutrons, with neutrons that, okay, they're not being repelled by electromagnetic interaction, but what is actually holding them together? They're not being held together by electromagnetic interaction either. So you've got to have something which is holding all this stuff together, and it needs to be stronger than the electromagnetic repulsion in order to hold protons in place. So clearly we've got some other interaction, some other force which is holding this in place. So now we've got a system of objects with energy based on position. If we've got all of these nucleons and they're being held together with various forces, then we've got a system of nucleons, forces holding them together, which means energy. So if we've got a system with energy based on position, this is all potential energy we're looking at here. We've got a whole load of potential energy which is sitting inside this nucleus. So much so that with the strength of the strong interaction, it's not called strong for without good reason. We've got lots of energy, and as we've seen, energy has mass associated with it in our mass energy equivalence. So the strong interaction is so strong relative to the invariant mass of these neutrons, i.e. nucleons, so when I say invariant mass, I mean the mass you get in a particle without including other forms of energy. So without including kinetic energy or potential energy, what is the mass of the particle. That's the invariant mass. That's the bit that doesn't change. Otherwise the mass of the particle is changing with the energy it has. So this strong interaction is so strong that about 95%, even more, of the mass of the nucleus is coming from this potential energy. So that is huge. It's swamping the invariant mass of these nucleons. So, and it's playing around with this potential energy that is that's at the heart of nuclear reactions, the energy release, nuclear fission, nuclear fusion, and things like that. Because if we take a close look, and okay, we won't go into the details of all of this because it's far too complicated, but this is the sort of stuff that's inside quantum chromodynamics. We're happy enough that in an atom we've got a nucleus with various shells of electrons. The electrons arrange themselves in certain ways around the nucleus, and they do that to make themselves more stable, to get into low energy states. You get a similar thing happening inside the nucleus, where these protons and neutrons can arrange themselves inside shells in a sort of analogous fashion to what's going on with the electrons. And because they can arrange themselves in different ways, then they're also looking for this low energy state, and the potential energy is changing around. Now that can either happen just inside one nucleus. You might get a beta decay or something. You might get rearrangement of these. You might get an electron chucked out from the nucleus, and a neutron changes into a proton. Everything rearranges a little bit more, and you've got some energy has been thrown out. Now, the energy of actually creating this electron and the kinetic energy that it has for leaving the nucleus, so there's energy coming out of the nucleus here, that is because the potential energy has changed inside the nucleus. So that's what we've got going on inside here, and why the strong interaction is so important. Now, we're only looking at this level inside nuclear physics at the how do we get energy release in fission and fusion in these different nuclear reactions, well, and in radioactivity as well. So we've got all of these things. Where is the energy coming from? Obviously we're not looking at quantum chromodynamics at the moment, which has a much more detailed description of all of this stuff. We're not concerned about that. So let's have a look then at the binding. Oh, actually, before moving on to the binding energy, let's say a little bit about the range then of the strong force. I'll squeeze in a little graph over here. So say we were going to plot out the strength, so something to do with a force here, the strength of the force with distance, then you get some kind of behavior a bit like this, and this is over very short range. So if you're below around about half a femtometer, so remember femto is 10 to the minus 15, so we're looking at 5 times 10 to the minus 16 meters. So you're in this area here. The strong interaction is actually repulsive. It then becomes attractive in this region. It's sort of peaking around about 1 femtometer and going to maybe 3 femtometers. So this is very, very short ranged, but very strong. So this is dwarfing by maybe a factor of about 1,000 the electromagnetic interaction when you're getting into the heart here of the attractive part of the strong interaction. But the very short range is placing a limit on the size of a stable atomic nucleus, because once we start getting up to 3 femtometers or thereabouts, the electromagnetic interaction is going to start to dominate, and the repulsion is going to start to dominate over the attraction, because the attractive force that is in the strong interaction has dropped down to next to nothing by the time you've got to that range. So if an atomic nucleus gets too big, it will start to become unstable, which is why those elements at the top end of the periodic table, these are things that get created in the lab in some way, and they don't last for very long and immediately start decaying. So you do have that limit going on there. So right, let's push on then with looking at some binding energy and mass defects. So as I was saying, we're talking about potential energy here is at the heart of all of this. And binding energy, this is potential energy that we're looking at here. So the binding energy, let's make a comparison to gravitational potential energy. So if we've got, and we've done all this before, you've got the Earth, you've got some object on it, they're gravitationally bound to each other, they attract each other. And we were saying that we were defining that if you separated these two objects so that they were infinitely far apart, like this theoretical idea that they're no longer gravitationally attracted to each other, then we say the potential energy is equal to zero, which is why you get this idea of, you know, what people refer to as, you know, these gravitational wells and things, where we've actually got negative potential energy when they're bound together. Because if we've got zero here at infinity, you've got some object at infinity and you let it, because it's getting attracted to the Earth, you're not having to do work here, this will just get more and more closely bound, and then it ends up with negative potential energy because you need to put energy in to get it back again, to get it back to zero. You know, we don't have to put energy in to get it down here. You know, in fact, we need negative energy to go in to just get it down there. But you have to put energy in to get it back again, back to zero. So this potential energy, this gravitational binding energy, is negative. We've got the same thing, exactly the same idea happening here in nuclear physics. So we've got this idea that if you had two, or say it was a proton and a neutron, and they were infinitely far apart, and you then brought these together, then, well, the strong force, you know, there is no repulsion at all that's going on. And once you get them close enough, the strong force kicks in, they bind together, and you get that negative potential energy because they're bound. And we see these sort of things happening all the time. I mean, this is, you know, part of what we'll see. If you did this and they bound together, you then get an energy release. You'll get, you know, a photon would get released. We see similar things happening with the proton-proton chain in stars. So you add two protons together, you know, we can bring those together and bind them into some kind of state. Now, that's not a stable state because the protons being the same type will clash a little bit in terms of the Pauli exclusion principle. This is something we'll talk about more when we get onto quantum mechanics. So it's actually more stable. Remember, we want to get into the lowest energy state if possible. If we had a proton and a neutron, because then they're different particles, so they don't clash on Pauli exclusion principle, and they can get into even lower energy states. So we'd have that, but then of course we'd need to chuck out a positron as well as an electron neutrino. And this is something that goes on inside of stars all of the time. So what we want to get the idea of here is this binding energy is negative, and the more bound, so more bound means more stable, which means that we've got a lower, so a more negative potential energy, which means we've got a higher binding energy. And this is the thing which can confuse people. So the definition of the binding energy is not the value of the negative potential energy, it's the energy required to take all of the nucleons that are bound and separate them to infinity. So it's actually the negative of the potential energy. So we're taking the negative potential energy value and we're making it positive because it's the energy that we need to put back in order to split everything up. And this can cause a little bit of conceptual confusion in people. So a lower energy system, which is what we want. So yeah, more negative potential energy means lower energy, which means higher binding energy. So that's what you really need to get clear in your mind, that low energy system means higher binding energy. And it's this change in binding energy that gives us the energy release and then what's known as mass defect. So let's consider these like this proton and neutron. So we've got this proton and neutron at infinity. You've got some mass of the proton, you've got some mass of the neutron. They're both just sitting there. These are our invariant masses. So we're saying these have got no energy. There's no kinetic energy in either of these things. Both of the particles, they're not moving. They've got no potential energy. They've got no kinetic energy. They're just sitting there with their invariant mass. If you then bind them together, the new system that we've got of the proton and the neutron bound has got the same two invariant masses, plus it's got this negative potential energy. So it's now got less energy in the whole system than it did before. From our mass energy equivalence, that means the overall mass is less because energy has got mass associated with it. That difference in mass is the mass defect. So when you move to a more stable situation, all of these equations that we look at, when you see these things like, proton plus proton goes to, deuterium plus a positron plus electron neutrino, all of these things, you're going to have more mass sitting in the ingredients on the left hand side than you are in the sort of ultimate product on the right hand side. And the difference in the mass, you've got some mass here, M1, some mass there, M2. The difference in the mass defect, is going into the energy that's been released. So the release in energy, you have to be a little bit careful about what we're including in all of the mass. So you might include the mass of the positron in all of this as well. It depends what you're going for. If you're looking at a mass defect between these two things, or are you looking at a mass defect between all of that? But one way or the other, whatever's missing, whatever's changed, in that we've got two nucleons here and two nucleons there, and yet we've still got other stuff, the energy to create this other stuff and give it the kinetic energy to leave, that's all come from this mass defect, which is the difference in the potential energy, which is also the difference in the binding energy. So there's a lot of ideas to try and, pull all of this apart. And this is why we're then looking at, if you look at the other end, so let's just slightly jump ahead for what we'll be talking about in a future video. You've got some unstable uranium. So it's a big nucleus. It's got, 238 nucleons or whatever, depending on the isotope. It's unstable. So it's not that strongly bound. It's still got negative potential energy, but it's got a relatively low binding energy. So it then splits into two smaller nuclei. These two nuclei are more tightly bound. They are more negative in their potential energies. So they've got higher binding energies, which means we've got a difference there in the invariant masses plus the potential energy has changed. So we're going to get a mass defect. If you actually weigh this nucleus versus that one plus that one, you've got a difference in mass. That difference in mass means a difference in energy, and it's that energy that has been released, which might be released in the form of fast-moving neutrons. So you'll have high kinetic energy neutrons that have been released out of this. Maybe some photons as well. You've got all manner of stuff that's going on. So this is what we're continually wanting to add up in all of this, that we're looking at, well, what is the binding energy of each one? So for each nucleus, we're normally describe them in terms of binding energy per nucleon. Nucleon, if I can write that properly. So binding energy per nucleon. So then we can say, what is the total binding energy of each one? And then that allows us to work out mass defect. So this is at the heart of all of the calculations that we're going to be doing. I'm going to do the next couple of videos on nuclear fusion, nuclear fission. So, combining atoms and splitting atoms. Then we'll work out binding energy, we'll work out mass defect, and then we'll work out energy release. So you can say for every single reaction that happens, this is the amount of energy that gets released. And that's how nuclear power stations can, power things for us, if only they build a few more of them. So this will become a lot clearer in the context of calculations that we're going to do. At the moment, just try and get your understanding clear on what all of these things actually mean. So the potential energy, the binding energy, and the mass defects. Just make sure you understand really what those are referring to. All will become clear.